we will see how to differentiate hyperbolic cosecant inverse function. First, I will derive cosecant inverse x, hyperbolic cosecant inverse x function, and then we will look at the differentiation of that basic cosecant inverse x function. And after that, we will look at how to differentiate hyperbolic cosecant inverse function when it's given as a composite function. So the first step is to obtain this function, hyperbolic cosecant inverse x function. In order to obtain that, I will write down first the hyperbolic cosecant x function. This function is equal to 1 over hyperbolic sine x. Therefore, it should be equal to 2 over e to the x minus e to the negative x. We will write this function as y equals, and in order to find hyperbolic cosecant inverse x, I need to switch x and y, and then I need to subject y. So if I switch x and y, this equation is going to be x equals 2 over e to the y minus e to the negative 5. And then I need to solve this one and subject y. I will multiply both sides of this equation from e to the y minus e to the negative 5. On the left hand side also I will have e to the y minus e to the negative 5. When I do this multiplication, on the left hand side I have x times e to the y minus e to the negative 5. On the right hand side you can see that these two terms can be divided out. Therefore, on the right hand side I just have a 2. Now I need to simplify this one a little bit more, and in fact I will multiply both sides of this equation by e to the y. When I multiply both sides of that equation by e to the y, the first term is going to be x times e to the y times e to the y, which is e to the 2y. So it will be x times e to the 2y. And the next term is x times e to the negative 5 times e to the y. E to the negative 5 times e to the y is equal to e to the 0th power, which is equal to 1. Therefore, it simplifies to become x times 1. And there's this negative symbol, therefore it will be just a negative x. I will write it as the last term. On the right hand side, I have a 2. When that 2 is multiplied by e to the y, it will be 2 times e to the y on the right hand side, which I will write on the left hand side as negative 2 times e to the y. And we have one more term left from the left hand side, which is e to the negative y times x times e to the y, which we said is going to be equal to just negative x. All of this is equal to 0. This is a quadratic equation of e to the y. And I need to identify a, b, and c in order to use the quadratic equation formula. We can see that a is equal to x and b is equal to negative 2 and c is equal to negative x. We know the solution is given by, in this case my variable is e to the y, therefore e to the y should be equal to, we know it's negative b plus or minus square root b squared minus 4ac, everything divided by 2a. Since b is negative 2, negative b will be equal to a positive 2 plus or minus square root b squared, which is negative 2 squared minus 4. A is x, c is negative x. All of that's inside the square root. All of that need to be divided by 2 times a, 2 times x, because a is equal to x. Now we need to simplify this one some more. You can see that e to the y is equal to 2 plus or minus, inside the square root I have negative 2, everything squared is a positive 4, and this part will be simplified to become plus 4x squared. All of that should be divided by 2x. We can simplify this some more. E to the y is equal to, from inside of the square root I can factor out a 4. If I factor out a 4 from inside of the square root, it will be 4 times 1 plus x squared. Then this 4 will get out of the square root as a 2, and from all of that I can factor out a 2. When I factor out that 2, the first term is a 1 plus or minus square root 1 plus x squared. All of that should be divided by 2 times x. Now I can do some further simplifications. The 2's can be divided out from the numerator and the denominator respectively. then e to the y is equal to 1 plus or minus square root 1 plus x squared, all of that's divided by x. We know that e to the y should be positive. So how do you get e to the y to be positive? What symbol from these two should be selected? Well, that can be actually discussed under two situations. One situation is when x is greater than 0. If x is greater than 0, the denominator is eventually positive, and I need to make sure that the numerator is also positive because I need e to the y to be positive. Since 1 plus x squared, for all real values of x, it's more than 1. If it is more than 1, and if I have to subtract that from 1, then that numerator will be equal to a negative value. Therefore, when x is positive, my e to the y should be equal to 1 plus square root 1 plus x squared, all of that's divided by x. Next, we will see the case where x is negative. If your x is negative, then we know that the denominator is negative. However, it is still e to the y equals. E to the y is always positive only because e is a positive number. So e to the y for all values of y should be positive. Now, when x is less than 0, because the denominator is negative, I need the numerator also to be negative. Then only negative divided by negative will become a positive value. Therefore, I need to select the negative symbol in that case because 1 plus x squared, for all values of x, it's going to be larger than 1. For the entire numerator to be negative, I'm going to select the negative symbol when x is less than 0. Therefore, let me write down e to the y as 1 minus 1 plus x squared, all of that's divided by x. This is for the case where x is less than 0. So we have two functions basically, but this is not all. We still have to do some further calculations because we need to subject y. So how do you subject y? These equations are always written as e to the y equals. No matter whether x is greater than 0 or x is less than 0, I have to take natural logarithm. So when I take the natural logarithm, we will still have two different equations. So let's look at the case where x is greater than 0. Then y will be equal to natural logarithm, all of that, 1 plus square root 1 plus x squared divided by x. And when x is less than 0, from the second relationship that we have obtained, when I take natural logarithm, I get y equals natural logarithm 1 minus 1 plus x squared square root. All of that has to be divided by x. So now we have derived hyperbolic cosecant inverse x function, cosec inverse x. We have two different equations. One is for the case where x is positive, the other one is for the case where x is negative. When x is positive, we have natural logarithm 1 plus square root 1 plus x squared, all of that's divided by x when x is greater than 0. When x is less than 0, we have the other function, natural logarithm 1 minus square root 1 plus x squared, all of that's divided by x. That is for x less than 0. All right, now we need to differentiate hyperbolic cosecant inverse x and see what results that we are going to obtain. We will look at these two cases separately. I will first look at the derivative when x is greater than 0. That means I'm going to first differentiate this first part of that function. For that interval x greater than 0, d by dx cosec inverse x should be equal to d by dx ln 1 plus square root 1 plus x squared, all of that's divided by x. When I differentiate that, what will I get? Since x is positive, if necessary, I can split that into two pieces using the properties of natural logarithm before doing the differentiation. Therefore, let me write this down as d by dx. When I apply the natural logarithm properties to simplify this part, it's a quotient and I need to take the natural logarithm. Remember, natural logarithm m divided by n this is equal to natural logarithm m minus natural logarithm n. Of course, it doesn't necessarily have to be natural logarithm. For any base, any logarithm will show this characteristic. Therefore, if necessary, I can use that property and simplify that natural logarithmic function to be differentiated. Therefore, I'm going to write this down as natural logarithm 1 plus x squared square root, that minus natural logarithm x. I can do that because we have this condition x greater than 0 for this function. Let's go ahead and do the differentiation. When I differentiate this function, I need to first differentiate this first part. Remember, natural logarithm differentiation, if I have ln f of x to be differentiated, this is equal to 1 over f of x times f prime x. So ultimately, you can write it as f prime x over f of x, where f prime x is the first derivative of f of x. So for this first function, we need to see this part as our f of x. That should go to the denominator, and therefore let me write it down as it is 1 plus square root 1 plus x squared. On the numerator, I need to differentiate that function, this part. That was the one that I selected as f of x. If you differentiate the 1, it's going to be 0. Therefore, practically, I only need to differentiate this part. I need to use the power rule when we differentiate that part. So I need to identify that as 1 plus x squared, everything raised to the 1/2 power, which I will simplify as 1/2 times 1 plus x squared raised to the 1/2 minus 1, which will simplify to become a negative 1/2. That times the stuff inside should be differentiated. I need to differentiate 1 plus x squared. 1 becomes a 0. When you differentiate the x squared, it becomes 2x. And then I have one more component left. I need to differentiate natural logarithm x. When I differentiate that, we know that it's going to be 1 over x. Now we need to simplify this. You can see from the first fraction, this 2 is in the denominator and this 2 is in the numerator. Those two 2's can be divided out, and then that numerator can be identified as just x over square root 1 plus x squared. All of that should be divided by 1 plus square root 1 plus x squared, and that minus 1 over x. Now we need to simplify all of that. How would you simplify them? Let me first consider this part, this first fraction, and both top and bottom. I'm going to multiply them by square root 1 plus x squared. When I do so, this is going to be now equal to, you can see that from the numerator, the square root 1 plus x squared and the square root 1 plus x squared can be divided out. Therefore, on the numerator, I will only have an x term, and in the denominator, I have inside parentheses 1 plus square root 1 plus x squared times another square root 1 plus x squared, and that minus 1 over x. So I need to simplify that further. When I simplify these two fractions, I once again need to take them into a common denominator. That means this first term, first fraction, should be multiplied by x, both top and bottom, and the second fraction, 1 over x, should be multiplied by all of these things, both top and bottom. That means I need to multiply that by 1 plus square root 1 plus x squared times square root 1 plus x squared. I need to multiply both top and bottom by that. So let me write it down one more time. 1 plus square root 1 plus x squared times square root 1 plus x squared. Now we need to simplify all of that. When we simplify all of that, we have a common denominator, which I will write as x times 1 plus square root 1 plus x squared times square root 1 plus x squared. On the numerator, from this first term, I have x times x, which is simplified as x squared, minus I have 1 plus square root 1 plus x squared times square root 1 plus x squared. Now I'm going to simplify it some more. I have all of this in the denominator. Let me copy and paste. That will be easier for me. That's your denominator. And now I need to write down the numerator. The first term is just an x squared. And then I have this negative symbol right here. Let me write that down. And I need to distribute square root 1 plus x squared into each of these two terms inside that next factor. Square root 1 plus x squared times the 1 is going to be square root 1 plus x squared. And please do not forget that this negative symbol is common to both of these terms. Therefore, when I distribute that negative symbol to that second term and multiply this square root 1 plus x squared with the other square root 1 plus x squared, they will become just minus times 1 plus x squared. Now we need to simplify it some more. You can see that this is a positive x squared and this x squared has this negative symbol. Once that negative symbol is distributed, those two terms will be cancelled out. And on the numerator, I have negative 1 plus x squared minus 1. In the denominator, I have x times 1 plus square root 1 plus x squared times 1 plus x squared. Then from the numerator, you can see that I can factor out a negative 1. When I do so, I have square root 1 plus x squared plus 1. And in the denominator, I have x times 1 plus square root 1 plus x squared times square root 1 plus x squared. You can see that these two terms can be divided out from the numerator and the denominator respectively, and therefore this final answer is going to be equal to negative 1 over x times square root 1 plus x squared. That is the differentiation of hyperbolic cosecant inverse x when x is greater than 0. So let me write it down. D by dx cosec inverse x is equal to negative 1 over x times square root 1 plus x squared if x is greater than 0. However, we still have to derive the first derivative of this function when x is less than 0 as well. So what was the hyperbolic cosecant inverse x when x is less than 0? We go back here. We had these two functions. What we took care of right now is the case where x is greater than 0. We still have to look at the case where x is less than 0. When x is less than 0, hyperbolic cosecant inverse x is actually equal to this function right here. Natural logarithm 1 minus square root 1 plus x squared, all of that's divided by x. We need to differentiate that function also and see what we are going to get. And we have to keep in mind that we are going to look at the case where x is less than 0. All right, let me copy this function real quick. That's our hyperbolic cosecant inverse x when x is less than 0. For x is less than 0, hyperbolic cosecant inverse x is equal to, let me paste that function. We'll have it in red. All right, now I need to differentiate this function, and I need to keep in mind that I'm looking at the case where x is less than 0. When I differentiate that, d by dx cosec inverse x, in this case on the right hand side, d by dx natural logarithm 1 minus square root 1 plus x squared, all of that's divided by x. Unfortunately, in this case, I cannot apply the properties of logarithm and simplify this right hand side. We cannot do that because if I do so, I will have a minus ln x term, which is undefined when x is less than 0. In fact, for this case where x is less than 0, unless I consider both of these components together, that ratio is not going to be equal to positive, because the numerator is negative, the denominator is also negative. That's how that quantity becomes positive. If that quantity is not positive, we cannot put natural logarithm there. So I need to differentiate that function also, keeping everything together. When I differentiate that, it's an ln function. Once again, I have to put 1 over all of that function, which is 1 minus square root 1 plus x squared divided by x, that times the derivative of that function, because I have considered this as f of x. That's how you will differentiate ln f of x. It's going to be 1 over f of x times f prime x. So I need to differentiate this highlighted part, this part. When I differentiate that part, it's a quotient. So I need to apply the quotient rule. When I apply the quotient rule, it's going to be the denominator times, that means the x times the differentiation of the numerator. If you differentiate the 1, it's going to be a 0, and there's this negative symbol. Let me write that down. And I need to differentiate the square root 1 plus x squared term. Using the power rule, it will be 1/2 times 1 plus x squared raised to the negative 1/2 power times, I need to differentiate the stuff inside the square root. That's the power rule. Then it will be times 2x. That's it from that first part of the quotient rule. And then we will have minus numerator times the derivative of the denominator. So the numerator is just 1 minus square root 1 plus x squared. That times the derivative of the denominator, which is the derivative of this term x, which is a 1. So I don't need to write that down. And then all of that should be divided by the denominator squared, x squared. That's the quotient rule. Now I need to simplify this function. For this first part, what I'm going to do is I'm going to multiply both top and bottom by x. So there will be an x written here, there will be another x written here. So that first part is now completely taken care of. This is going to be equal to, the numerator is going to be just an x. In the denominator, you can see that this x and this x can be divided out. Then that denominator becomes 1 minus square root 1 plus x squared. And then we have big brackets. All of that should be divided by x squared. And then on the numerator, I have to do some further simplifications. If I look at this first part of that numerator, you can see that I can divide out the 2 here and the 2 there. And I will still have an x term, and there's this negative symbol also. And this x term should be multiplied by the x term outside. And it will be negative x squared on the numerator. And that should be divided by the square root of 1 plus x squared. That is still in the numerator. So let me write that down. Square root 1 plus x squared. That is that first term. That's it about that first term. And then I need to subtract this term. Let me write that down. Minus 1 minus square root 1 plus x squared. Close parenthesis, close brackets. We can do some further simplifications for this statement. You can see that one of the x's from these two places can be divided out. In the denominator, I have x squared, so one x can be divided out, and this x will be gone, and it will be 1 over. Now we will do the simplification. This is now going to be equal to 1 over. Let me write down this x also outside, no problem. With that other term, x times 1 minus square root 1 plus x squared. And then inside brackets, I have negative x squared divided by square root 1 plus x squared minus, within parentheses, 1 minus 1 plus x squared square root. Close brackets. Now we need to do some further simplifications. When we do some further simplifications, I can assume that this term also has a 1 in the denominator. I need to convert that into a common denominator, which means top and bottom of that term should be multiplied by this other denominator, which is square root 1 plus x squared. I need to multiply both top and bottom by that. Let me write it like that. Do not forget to distribute this negative symbol. That is valid for this term. Now we will do the simplification. This is equal to 1 over, the first term is x times 1 minus square root 1 plus x squared, brackets. Now all of that inside the brackets have the same denominator, therefore I don't need to write two separate denominators. Let me write down just one denominator, square root 1 plus x squared, and the first term is a negative x squared term, and that minus, I need to distribute this term square root 1 plus x squared into each of these two terms, and I shouldn't forget the negative symbol. So let me open another bracket so that I can distribute that negative symbol later. This negative symbol is written right here. I will multiply square root 1 plus x squared with the 1, then I get square root 1 plus x squared, and there's another negative symbol right here. Let me write that down, and I need to multiply square root 1 plus x squared with another square root 1 plus x squared. Then the square root will be cancelled, which means I can write that down without the square root symbol, but that 1 plus x squared is together, therefore let me write it inside parentheses, otherwise I will forget to distribute this negative symbol. Let me close that curly bracket, and let me close the big brackets as well. Now I can do some further simplifications. All of this is equal to 1 over x times 1 minus square root 1 plus x squared, big brackets. In the denominator I have square root 1 plus x squared. On the numerator, the first term is negative x squared. Let me write that down, and then I need to distribute this negative symbol to each of the two terms inside the curly brackets. When I do so, the first term is negative square root 1 plus x squared, and then this negative with this negative will make it a plus 1 plus x squared. Now we can do some nice simplifications. You can see from that numerator that this is a negative x squared term, this is a positive x squared term. Those two will be added, they are like terms, and they will become 0. Do not forget there's this 1 right here, and this term is a negative square root 1 plus x squared. So let me write down those remaining terms. This is now equal to, on the numerator I will have 1 minus square root 1 plus x squared. All of that's divided by, there's this x right here, times the other factor 1 minus square root 1 plus x squared, and then I have this term. Let me write that also down, square root 1 plus x squared. Now you can see that we can divide out those two factors from the numerator and the denominator. This factor and this factor can be divided out, and there will be a 1 remaining on the numerator. So this is going to be finally simplified to become equal to 1 over x times square root 1 plus x squared. This is the derivative of hyperbolic cosecant inverse x function, cosec inverse x, if your x is negative. Look at this. This is equal to 1 over x times square root 1 plus x squared. We obtained this result for x less than 0. This is also another important result. However, remembering two results under two different scenarios, such as x greater than 0 and x less than 0, is a little bit difficult. Therefore, we will see if we can combine these two results. Earlier, we obtained the first derivative of hyperbolic cosecant inverse x function for x greater than 0. Let's copy and paste that one. This is that result. I'm going to copy and paste that result. So here's the result for x is greater than 0, and earlier we saw the result for x is less than 0. Hyperbolic cosecant inverse x. If you differentiate when x is greater than 0, you get a negative answer right here. All of these x's are positive. If x is less than 0, what do you get if you differentiate hyperbolic cosecant inverse x function? Is this a positive answer? It is not a positive numerical value. When x is less than 0, you can see that right here this x term is going to be a negative numerical value. Therefore, this result also is going to give me something negative. If your x is greater than 0, this is going to be a greater than 0 quantity, but all of that function is still negative. Therefore, essentially, if you differentiate hyperbolic cosecant inverse x function, your answer is going to be negative. Therefore, we can combine those two results and write down one nice result. d by dx hyperbolic cosecant inverse x. This should be equal to, let's write it as always negative, negative 1 over the x term. I'm going to write it inside absolute signs. And then inside square root, I have x squared plus 1. Now, for all the values of x, as long as x is not equal to 0, we get a negative answer as the derivative. So please remember this result. This is what you get if you differentiate hyperbolic cosecant inverse x function. We can also extend this result for a composite hyperbolic cosecant inverse x function. How do you extend this result for a composite function? We can write this as d by dx hyperbolic cosecant inverse f of x. That should be equal to, first we will differentiate this function with respect to f of x, and that times the derivative of f of x, which is f prime x. Then this is going to be equal to negative 1 over absolute f of x times square root f of x everything squared plus 1, all of that times f prime x. That times f prime x can be written by combining with this negative 1 as negative f prime x on the numerator. Therefore, let me modify this negative 1, negative f prime x. So this is your final result for the differentiation of a composite hyperbolic cosecant inverse x function. We will also look at an example. Let's say we need to differentiate y equals hyperbolic cosecant inverse 3x minus 2. dy by dx should be equal to, we need to identify that f of x is equal to 3x minus 2. Therefore, the answer should be on the numerator, I will have a negative symbol f prime x. Differentiation of 3x minus 2 is going to be equal to a 3. And in the denominator, I have this absolute sign. F of x is just 3x minus 2. That times, I have a square root symbol and f of x everything squared, which is 3x minus 2 everything squared. And then there's this plus 1. That's the final answer for that problem. If you like, you may go ahead and do some further simplifications inside the square root. However, this is accepted as a final answer for this problem. Alright, that's a bit long video, a complicated concept, but if you can simply remember these two results for the differentiation of hyperbolic cosecant inverse x and for the differentiation of hyperbolic cosecant inverse composite functions, that's basically all you need to know from the Calculus 1 class. Derivation of these results is actually not super important unless you are a math major. Alright, thank you so much.